Hi, we're Team 47, and our project is a low-cost ion-selective sensor for hydroponics solutions.
First, some background on our current agricultural systems. The recent outbreak of COVID-19 has demonstrated the unsustainability of our modern agricultural systems. We are currently dependent on complex and geographically expansive supply chains to meet the demand for international and non-native foodstuffs. In fact, the United Nations Food and Agricultural Organization has stated that if the current outbreak continues, it will severely impact the availability of fresh fruits and vegetables for the modern consumer. All this together highlights the need for sanitary and local food production. Zooming out from the current pandemic, the picture doesn't become much better. The global population is expected to rise to almost 10 billion people by 2050, and current food insecurity rates are actually also on the rise. The FAO again states that the growing population dynamics and food production and distribution are going to be central to global economic, social, and environmental development. And this has been motivating a lot of research over the past half century into more efficient agricultural techniques. And to further confound this problem, the amount of arable land globally has been decreasing significantly over the past century. Because of all of this, there has been an increased interest in alternative farming methodologies, particularly in closed system agriculture. These are systems where produce is grown in isolation from the exterior world, allowing growers to precisely control temperature, nutrients, fertilizers, etc. And one of the primary advantages of closed environmental agriculture is that the growing process is inherently sanitary, and farming stations can be constructed more freely without a heavy reliance on local climate or land quality. Our team took a look at the most popular or most commonly used closed system agricultural technique, hydroponics. Hydroponics is an agricultural technique where water is used instead of soil as the primary mechanism for nutrient delivery. The root systems of crops are supported by some inert medium, such as perlite or gravel, with water being used as a solvent for mineral and nutrient solutions, which are supplied to the root systems. Hydroponic systems are already utilized across the globe, including in the United States, and many have already shown great commercial viability. Successful management of hydroponic systems involves containing all fertilizers, pesticides, and agrochemicals within the system. As a result, many growers opt to recycle nutrient solutions by circulating the irrigation solution through the growing tanks, rather than simply disposing of it. However, before these solutions can be recycled, it is necessary to verify that the concentration of all the required nutrients is within the optimal range for the crops being grown. These measurements are typically done by sending solution samples to professional laboratories, which prevents growers from obtaining real-time information about their crops, and thereby making them less reactive to changes in nutrient concentration. Optimization of this task can provide growers with increased data on their crop's nutrient uptake, and it can pave the way to autonomous growing systems.
Nutrient sensing is critical to a hydroponic system, and there are two primary methods. One option is the ion-selective electrode, which produces an electrical potential by converting the activity of ions dissolved in a solution. The potential can be measured using voltmeter. There are various types of ISEs, and they are rooted in the principle of ion-selective membranes. They are, however, substantially expensive for large operations and require consistent maintenance due to deterioration. Another option would be to use colorimetric reactions and utilize specific compounds to generate a certain color spectrum corresponding to particular concentrations. Most colorimetric reactions have to be manually read against references, and in this way don't offer exceptional precision.
This project's objective is to develop a cheaper, more reliable ion-selective sensor for the macronutrients in hydroponic solutions. We aim to do this by standardizing colorimetric procedures for the ionic forms of macronutrients and precisely quantifying the results with computer vision. Our overall system design can be broken down into 4 parts. First is the colorimetry. We had to identify the relevant color reagents and colorimetric procedures that would allow us to test for the concentrations of desired macronutrients. The next part is the apparatus for solution processing. This involves the collection of representative samples of hydroponic solution, the automation of all chemical procedures with peristaltic pumps, and the appropriate disposal of waste and all byproduct. Next we have the camera and lighting apparatus, which is designed to eliminate all ambient light and standardize the lighting of our color reactions for taking images. Finally, we have the data processing section, which involves the translation of image color data into nutrient concentration readings.
With colorimetry, there are numerous established methods in determining concentration of macronutrients. Standard tests exist for ammonia, nitrates, orthophosphates, and potassium. For nitrates, we would use the cadmium reduction method and reaction with ferrous sulfate, which produces a brown-colored compound. Some proprietary solutions include the Hack Nitrover test kits and API nitrate test kit. For potassium, a proprietary solution is made by Easy Life International. This test provides a color spectrum over a range of 0 to 25 parts per million. For orthophosphates, we would use the absorbic acid test, which forms a molybdenum blue compound. We would be able to use the Hack phosphor test kit for this. For ammonia, we can use the salicylate test, which utilizes hypochlorite solution and sodium salicylate to produce a light green color transitioning to blue with increasing concentration. API makes this ammonia test kit readily available. These colorimetric methods were chosen in an effort to minimize hazardous chemicals, waste, and complexity while preserving a broad color spectrum. Further considerations include temperature dependence and treatment of waste products.
In order to collect representative samples, it is important to make sure that the hydroponic system is thoroughly mixing its nutrient solutions. We also want to make sure that we're sampling from an area close to the hydroponics pump, which directly feeds solution to the crops. The peristaltic pumps that we're using to control our system have a flow rate between 19 and 100 milliliters per minute, which varies based on the speed of our motor. We're using pulse width modulation to adjust the average power supplied to these motors, thus varying their speed. The GPIO pins of the Raspberry Pi are capable of pulse width modulation, but they only output 3.3 volts. In order to vary the 12-volt supply we have for our pump motors, we need to use a FET, or field effect transistor. The particular FET we chose has a gate threshold of around 2.5 volts, which is perfect for this conversion. Our system design has two pumps, one which samples the hydroponic solution and another that adds the color reagent. These solutions are merged with the T-junction, and then fed into a series of loops and bends which induce enough turbulence to adequately mix the solution. We will separate segments of our solution with pockets of air to prevent cross-contamination of our samples.
In order to illuminate our sample, the solution will flow through two glass slides positioned in front of our camera, with the LED and light diffuser positioned behind it so as to shine light through our solution and into our camera. There were a couple of key considerations when selecting a light source for our system. The source had to 1. Produce light at a relatively constant brightness, and 2. Had to produce light within a spectral range that would allow us to take meaningful results. This meant that we needed a light source that would produce light within about 530 to 650 nanometers in wavelength, which corresponds to roughly the green to reddish part of the visible light spectrum. We selected this range because that corresponded to the expected colors of our final solutions based on the colorimetric procedures we selected. Additionally, we also had to ensure that there was no interference by any form of ambient light within our system. This meant that 1. We had to enclose the system in a physical box, and 2. We had to paint the interior of this box black so as to eliminate any form of internal reflection or interference in that way. Finally, the picture could then be taken with an 8-megapixel Raspberry Pi camera.
Let's take a closer look at the data and image processing portion of our system's pipeline. As mentioned, pictures are captured with an 8-megapixel camera which is powered and controlled by a Raspberry Pi. These images are saved somewhere where they will be manipulated using Python's imaging library, which approximates the color of the fluid in the chamber. Based on this image, we can determine the amount of solution that is needed to optimize the concentration of nutrients. For example, if the solution is orange but we expect a red color, we can determine exactly how much of a nutrient is needed to be added to the solution in order to achieve the optimal concentration of the nutrient for the plant. These calculations are converted to a signal which controls the peristaltic pumps in our system. When taking pictures and analyzing the color of our solution, there are some considerations we need to make when calibrating our camera. We need to account for any changes in light intensity, which can be a byproduct of LED age, inconsistent power sources, or even reflection within our black box. This requires us to maintain a consistent light exposure and white balance in our pictures over time to make sure that our calculations are always consistent. A common practice in photography is to use a neutral gray card with known color and reflective properties to maintain this white balance. As seen on the right, you can see two pictures before and after this white balance. We can achieve something similar by just simply applying a filter to our images using OpenCV and Python. Working remotely has been a bit of a struggle, but we've still been able to make considerable progress on our prototype. So far, we've completed the hardware aspect of our prototype, which includes a configuration for all of the pumps, pipes, and camera setup for testing. For the purpose of our prototype, we have been using the universal indicator, which measures the pH level of a solution. Our camera is able to correctly identify the different color regions and approximate these pH values based on the image. Currently, we're in the process of calibrating and testing our system with a universal indicator. However, we have identified standard chemical procedures that are compatible with our design that are useful for identifying the presence of different macronutrients in the solution. Once we have completed testing with the universal indicator, we plan to adjust our system to these procedures, which will allow us to further optimize the hydroponic system.
Our future ambitions for this project have two phases. First and foremost, we aim to replace the universal indicator pH test with the colorimetric reaction necessary to test for one macronutrient ion in a sample of hydroponic solution. We also aim to redesign our prototype by reducing its size, ensuring that it's environmentally compatible with the conditions inside greenhouses, and improving its accuracy with higher quality parts. As for the second phase, the ultimate goal of this project is to develop a product capable of determining the concentrations of all desired macronutrient and micronutrient ions in hydroponic solutions. We also aim to network with growers to better understand the demand for this technology and its viability as a marketable product.
We would like to acknowledge and thank the following people for their assistance and supervision throughout our project. Thank you.